guess let's just give it a minute for other people to arrive and then we'll start talking. How you guys doing after a nice long weekend?
Pretty good.
Hard to wake up early this morning, right?
Not that early. Yeah. I don't think 10 is bad.
You know, this is my third class of the day. So for me, like I've been going for a while now. It's kind of wild.
You start at 8, huh?
Yeah, my classes start at 8 this semester. Yeah. Although I don't have to commute to Boston, I'm teaching remotely, so that's nice. When I commute to Boston, I have to leave the house at 6 in order to get to campus because I take the train. So that, you know, is the train gonna run late? I need that extra window because sometimes I don't get to campus until like 7:30, but and that doesn't give me a lot of time to prepare. So I have to leave really early. I don't have to worry about that this semester. I'm teaching remotely, but still have to wake up earlier than I'd like. But whatever.
Yeah. I mean, if you're asking me, 10:30 is earlier than I'd like.
All right, I know. I'm not a morning person, but you know.
Yeah, I'm not a morning person at all. If I could, I do all my classes in the middle of the night.
Right. I know. That would totally work for me. Yeah. I don't know why Northeastern doesn't do that, but
yeah.
Anyway. Okay, you guys. So let's talk. So so first I'm still grading. So thank you for your patience on all that kind of stuff. I know you're eager to see how things went on the exam, but I'm still grading it. So I can't talk about that just yet. Also, if you take a look on our website, I posted a bunch of stuff for this week and next week. Now we have, let's see, we're starting chapter 2 today. 2.2 is what we're gonna go into detail on today. And then basically 2.2 homework will be due next week because we have a quiz on 2.2 next week. So that homework is due. You'll see the dates on the quizzes, on the homeworks and stuff. I'm posting, we're going to do 2.3 tomorrow, but 2.3 homework won't be due to the week after. So just going to take a look at when the due dates are for things on there too. The homework solutions, remember, are at the very top of our modules page, right? So at the very top under reading materials, I've got a whole bunch of stuff and homework stuff. I've got homework chapter 1, chapter 2, chapter 3. And on that, at the very top, it'll also say like the homework solutions for chapter 1 and chapter 2 and chapter 3. So you can take a look there. If you can access that, send me an email and I'll take a look and see what's going on. Hopefully the content is there. I had some trouble with my other classes where I posted a whole bunch of stuff and I think Canvas was doing things behind the scenes and it like ate it. So it looked like it was there, but there wasn't content behind actually in place. Even though the file upload showed that it had been uploaded, it was weird. So let me know if you can't access anything. You guys should be able to get the classwork for 2.2 and the lecture examples and all that for today and tomorrow, so we can work through things. And then certainly the homework. I want to call your attention to, I also had posted up for next week some information about our project. This is the project that's due at the end of the semester. And this is the project that we do in place of a final exam. You can work with a partner on the project. We have a small class, so partners, could work. You don't have to, you could work alone. I wrote up kind of like what we expect, to see for the write-up and for other stuff. And we're going to see what we can do about presentations. I think that'd be kind of neat if we can have some kind of presentations to see. It's always fun to see what everybody else is working on, but we can figure out how we're going to do that with the Zoom. How we'll do Zoom presentations so I can share the screen with other people and stuff. And then let me think. Yeah, so I think it's like November 5th or something like that. I'm trying to remember. I have a very preliminary assignment for project presentations. I counted it as 0 points, but it's just to kind of keep you thinking about it, where you're basically looking at maybe approaching somebody else. Do you want to work together on this? And also maybe coming up with, I'm going to say non-binding description of what you might like to work on. It's just to get you to think about like, oh, I want to do a game that's like Pong, and things bounce off, whatever. you're just coming up with a couple sentences describing what you want to work on. It's non-binding. So if you really describe all the stuff, you write a really detailed paragraph, start to get into it and you realize, hey, this is going to be a much more complicated thing, you can totally back out of it. Okay, but it's just to get you thinking so that you don't get to December and go, oh, I haven't done anything for the project. So keep that in mind. All that stuff is listed for next week's module. So take a look at our modules page and you'll be able to see some of that stuff. Okay, so we have a short week this week, but but there's a lot of interesting things happening. So let me first start talking. So we're in chapter 2 now. It's a really exciting chapter. This is kind of chapter 1 was really neat, where we talked about like certainly it's all like the math behind things, but in chapter 1 we talked about like intersections and projections and sort of the fundamentals for like the bare bones of like what's happening. Intersections and projections are pretty pretty bare bones. Now in chapter 2, what we're going to talk about is transformations. And this is pretty neat because what happens with transformations, what we mean by that is we're taking something, right? And we're going to reflect it across a surface, or we're going to project it onto a surface, or we're going to scale it so that I can make it bigger or shrink it, or I'm going to transpose it, so these are the kinds of things that we're actually going to be using when we try to display stuff on a screen, right? Say, for example, I have a balloon and there's a puddle on the ground and I want to show inside the puddle, I want to show the reflection of the balloon inside the puddle, right? And so how do I make that happen? So this is kind of like examples of things that we're going to be talking about. So transformations, so reflections, rotations, we're going to talk about. We're going to talk first. We're going to do all this stuff in 2 dimensions, right? X, Y plane. 2 dimensions are really nice and straightforward. And then we're going to extend the math towards the end of the chapter. We're going to extend the math to 3 dimensions. We do that because the math gets more complex. We start doing things in 3 dimensions. And so we have a lot more that we need to take into account. But we're going to detail all of the stuff in 2 dimensions first. So it's all kind of there in your mind. So then when we expand it to 3 dimensions, then it'll make more sense about like why we're doing it. Anyway, so when we talk about transformations, just sort of a really, really high level, we talk about things, we say T of X is our transformation, right? And then X is maybe, like our vector, right? I've got this, some kind of a component, a vector component that I want to use to represent things. Now, always when we talk about our transformations, like you remember at the very beginning of the semester, we talked about the Disney cartoon where Disney's on the steamboat and Mickey Mouse was on the steamboat, and then when they made these, they had to do like a little picture, and then they took a picture of it. They drew another picture of a slight movement, and they kept drawing all these pictures. Well, now with computers, what we want to do is we want to reduce everything down to component pieces, right? So so Mickey Mouse, like I can represent as a circle and then a couple semicircles, like for the ears, right? And so what I want to do, a circle really is just a center and a radius. So when I talk about moving the head from here to here, what I'm going to do is I'm going to take this picture, I'm going to reduce it down to my center point. I'm going to move the center point from here to here, and then I'm going to rebuild my circle, right, and resketch it. So we're always thinking, what are the really, really fundamental component pieces of the structure that we're working with, right? So if I have a cube, I only really need 3 vectors, my width, my height, and my my depth, right? So give me those 3 dimensions. I've got 3 vectors, now I'm going to move those 3 vectors, and I'm going to rebuild my cube around that, right? So you're always trying to be thinking about, I've got some, big structure, but how can I reduce it down into really simple components like vectors, say, for example, and then I'm going to do the transformation on the vector, and then I'm going to get some output, right? So this is just really generic. So this is our input, and Y is our output. And then T is the transformation function that we're actually doing. The point in all this, so we're talking, this is a math class, right? And I know my background is, computer engineering, but so we could code things up, and I think that'd be a lot of fun. But I was told by the math department to focus on math because you guys are getting coding and other building stuff in other classes. So we're focusing on the math, but we're always thinking about, right, when I talk about my transformation function, how can I like objectify that? I want to make it into a subroutine or an object in a piece of code, right? So that I can call that over and over again. So we're always be thinking in the back of your mind, oh, I keep doing this, process over and over again. I keep projecting, or I keep doing a dot product, or I keep doing a cross product, or I keep rotating by an angle. Say, for example, I'm going to make a program, like a subroutine or an object program, where I can just call that over and over again, and then I'm going to send it in an input of a vector, I'm going to get back an output of a vector. So always be kind of thinking about like what your code could be looking like. How can I put these things into object pieces, right? So I've got my transformation. T is the transformation that I'm trying to do. So I go from X to Y, right? Now there's a thing called the inverse transformation, which we write as T minus 1, right? And so what we would do is I would say I'm going to do this on my output, and it would get me back to my input, right? So this takes in the former output function, the former output, and returns us to where we started.
Is that the same as pressing Control Z?
I'm sorry?
Is that the same as pressing Control Z?
Control Z, like to return to where you like to go backtrack when you make a mistake on like a word processor. Yeah, you can think about it like that. Yeah, to undo what you've done, right? So this we can say we're going to undo. It's just like our undo button. And the difference is when we do this inverse transform, that not every transformation is going to have an inverse. Okay, many of the transformations that we're going to cover will have inverses, but not all of them will. So let me just write that down. So not all transformations will have an inverse. So some of these transformations are one-way street, right? I go down it and I can't backtrack. Many of them I can go down and I can come back, right? And we're going to actually discuss this, in this whole chapter. How do we tell if something has an inverse or if it doesn't, right? So chapter 2 is all about transformations. This is a really like high-level idea about it. But if we get into, this is all like chapter 2.1, just kind of talks about some of the vocabulary here. So 2.2 is where I'm going to be jumping in. Okay, so 2.2 is where we're actually going to be talking about it. Now, when we represent our transformations, there are many different ways to represent transformations, but when we do our transformations, we're going to represent them using matrices. Okay, so we're going to use matrices to represent transformations, which means I have to talk about what is a matrix, right? So let's talk about that first. Now, in linear algebra, we think about a matrix as a way of representing a system of equations, right? So this is way of representing a system of equations. So what do I mean by that? Like if I say I've got 2x plus 3y plus 4z equals 7, and then I've got another equation minus 3x plus 4y minus 6z equals 0, and then let's just go for broke. I'll do another one, 6x minus 2y plus z equals 4. So I've got this, what we call a system of equations. And this is a nice system because I have 3 variables, x, y, and z, and 3 equations, right? So I can actually find maybe a solution for this. And a solution would be, I'm finding a value of x and y and a z, possibly where these planes or these, lines interact. So now how we represent this, I'm going to strip out my x, y, and z, and I'm going to just represent it as numbers, the coefficients. So my first column is my x, so 2 minus 3, 6. My next column is the y, 3, 4, minus 2. My other column, my third column, 1, that's 1. There's a 1 there, even though we don't see it. And then what we tend to do is we write x, y, z. Those are our variables. And then we say this is equal to, what is this equal to? 7, 0, 4. So this is a matrix, this is a matrix, this is a matrix. These are all matrices, and they represent essentially how the system of equations interacts with one another. Okay, so at the really highest level, a matrix is how we represent a system of equations, and that basically represents a behavior of some system, right? These, and we talk about this in terms of planes or lines, but these could also be like, it could represent a circuit, it could represent a path of an object in space, you know, all sorts of things that you can think of to represent the system of equation. Okay, so now, so let's think about how we're going to talk about matrices. Now, we need to understand how we describe matrices and some of the mathematical things that we can do with matrices, so that then we can start describing our transformations as matrices, and then we know how to do the math on them. So the first fundamental thing that we think about with a matrix is something called a dimension. So the dimension of a matrix, right, is how we actually reference this. And this is, we say how many rows by how many columns, right? How many rows and how many columns do we have? So I look over here and I've got 1, 2, 3 rows by 1, 2, 3 columns. So this matrix here is a 3 by 3 matrix, row by column. Here I have 3 rows and I have only 1 column, right? So this is a row by column. Here again, I have 3 rows and a 1 column matrix, okay? So dimension is a really important concept when we talk about matrices. I'm going to pull out my lecture examples for 2.2 because these are kind of examples here, but I want to go through as we're doing things as we go. So looking at lecture examples 2.2, and I'm looking at example 1. What's the dimension of the following matrix, right? So the dimension, remember, it's row by column, right? So how many rows? I have 2 rows. I have 1, 2, 3 columns. So we would say this is a 2 by 3 matrix. Okay, likewise, for example 2, row by column. So how many rows? 1, 2, 3. How many columns? I only have 1. It's a 3 by 1 matrix. The dimension is super important because we use the dimension to answer questions like, can I do this, you know, mathematical thing, or can I do that mathematical thing? Some things are going to depend on dimensional matches in certain ways. Okay, so dimension, our first criteria, our first descriptor about matrices. Okay. All right, there's another thing. We'll call this a scalar multiplication. Like with vectors, you know how we can actually represent vectors and matrices are vectors have a whole rich component, but I can represent a vector as a matrix. We're going to talk about that as we go, but we use the same terminology. So scalar multiplication on a matrix. So when I do scalar multiplication, so if I have matrix A, say for example, and it's got stuff in it. It's, you know, I've got these, you know, rows and columns. I've got things in there, and I have a constant term, C. Okay, and if I want to multiply, C is like just some number. This is just a number. And I want to do a scalar multiple of C times A. What that means is, like I do with vectors, I take C and I multiply by every component in there. Now, in our matrix, I didn't tell you this before when I did dimensions, but in our matrix, we represent this spot here as the first row, first column. It looks like 11, but it means first row, first column. This here is the first row, second column spot. This here is the second row, first column, second row, second column. So depending on where you're at in a matrix, that spot has a name, right? And you can kind of think about this now. Look, I can think about how I can index a variable in a computer program, right, with this kind of a subscript, okay? So when I want to do a scalar multiple of my matrix, and I'm going to take my C, I'm going to multiply by every element inside of my matrix. This becomes C times A11, C times A12, C times A21, C times A22. So I just kind of distribute that scalar into every piece in my matrix. Like we did with vectors and scalar multiplication. We'll do matrix multiplication later in a minute, but right now we're just talking about scalar. So I'm looking at example 3. So this is, what's the following product? So 3 is our C term, and this is our matrix. This is like our A, right? First row, first column, first row, second column, first row, third column. My 4 is the second row, first column, second row, second column, second row, third column. Okay, so now I want to take this 3 and I'm going to distribute it to all of these terms in here. So it's going to look like 3 times 2, 3 times 0, 3 times a minus 1. I'll put that in parentheses so I don't get confused and think I'm subtracting. 3 times 4, 3 times 1, 3 times 3. Okay, so now I'm going to multiply it through. So 3 times 2 is 6. 3 times 0 is 0. 3 times minus 1, minus 3. 3 times 4 is 12. That's 3, and that's 9. Okay. I just distributed that 3 into every term in here. Example 4 is the same type of thing. Scalar multiple. Here's C and here's A. Here's our first row, first column, second row, first column, third row, first column position, right? So now when I go to multiply this through, I'm going to take the minus 2 and multiply it by each term in here. Watch out for your negatives. I have to carry that minus 2 into here. So that becomes minus 2 times 5. Minus 2 times a minus 2. Minus 2 times 1. Okay, now I'm just going to multiply it through. Minus 2 times 5 is minus 10. Minus 2 times minus 2 is positive 4, right? Minus times minus, that's a positive. Minus 2 times 1 is minus 2. Okay, and that's my matrix. When I do a scalar multiplication, it doesn't change the dimension of the matrix that I'm working with. And that's important because when I do matrix multiplication, matrix times matrix, the output may be a different shape. Okay, we're going to get to that though, don't worry about it. Scalar multiplication, it's just going to be distributing that number into each term. Okay. All right. Now we talk about addition and subtraction. So with addition and subtraction, I want to, so I've got matrix A plus or minus matrix B, right? Now, when I go to add and subtract, the first thing I have to check is what's the dimension of matrix A? It must be equal to the dimension of matrix B. Those dimensions must be the same. It's like when I go to add or subtract 2 vectors, right? Those 2 vectors have to have the same dimension because I'm going to add corresponding components together or subtract corresponding components together, right? The same thing with matrices. If they're not the same dimension, I'm going to have extra bits left over or not enough or something like that. It's not going to work. They have to have the same dimension. Otherwise, the thing won't work. You just say there's no possible answer. So now, if the dimensions are true, yes, this is true, then what I'm going to do is I'm going to add or subtract corresponding components. Right, so let's say, for example, matrix A was equal to A11, A12, A21, A22, and then matrix B was equal to B11, B12, B21, B22, right? They have the same dimension, 2 rows and 2 columns, 2 rows, 2 columns, both 2 by 2. So if I go A plus B, how that's going to look is like this. A11 plus B11. A12 plus B12. A21 plus B21. A22 plus B22. Okay, and this one, A11, B1, they're in the first row, first column. They stay in the first row, first column spot. Okay, so this add and subtract does not change the dimension of our output of our matrix. But you have to check. You have to check the dimensions. So if I look at example number 5, I'm kind of dealing with something like that. So example number 5 says, well, the first question it asks is this even possible? Right? So can I do the following addition or subtraction? Why or why not? So when I do this, right, I'm going to check. So I've got 2 rows by 3 columns. Ooh, look at that. I've got 3 rows by 1 column. The dimensions don't match. No, cannot be done. Because dimensions do not match. Right? Look at it. I'm going to add first row, first column. First row, second column. Well, there's nothing there. I can't do it, right? I'm just kind of left going, there's nothing there. So that means I can't do that mathematical operation. Okay. All right. Let's take a look. Can we do these first? We're always going to check. So this is 2 rows by 3 columns, 2 rows by 3 columns. Yes, I can add or subtract that one. So I'm going to do corresponding pieces, right? So this is going to be 2 plus 7, 0 plus 6, minus 1 plus a minus 10. I put that in parentheses, minus 1 plus a minus 10. Keep me honest in terms of my negatives. So 4 plus a minus 2, 1 plus a minus 1, 3 plus 5. Be careful, I'm not adding across the top, just adding in this little bit right here. This is my first row, first column. 2 plus 7 is 9. 0 plus 6 is 6. Minus 1 plus a minus 10 is minus 11. 4 plus a minus 2, 4 minus 2. 1 plus a minus 1 is 0. 3 plus 5 is 8. Okay. Let's see how we're doing that. Let's check this one. So we're subtracting now. There we were adding, we're subtracting here. So we're going to do the same thing, but we're just going to subtract. So let's check. I've got 2 rows by 3 columns. Rows by 3 columns. Good, so I can do this. All right, so let's set it up. So I'm going to go 2 minus 7, 0 minus 6. I can put this in parentheses, minus 1 minus a minus 10. This is the parentheses around the negatives are really important, right? Because it's going to help keep track of what do I do with these negatives. So 4 minus a minus 2, 1 minus a minus 1. Be careful because 1 minus a minus 1, right? So be careful about that, right? We already did 1 plus a minus 1. So 1 minus a minus 1. This is 3 minus 5. Okay. So first row, first column, 2 minus 7 is a minus 5. 0 minus 6 is minus 6. Minus 1 minus a minus. This becomes minus 1 plus 10, which becomes a 9. 4 minus a minus becomes 4 plus 2. That's 6. 1 minus a minus becomes 1 plus 1. 3 minus 5 is minus 2. Okay. So far, so good. I'm going to scroll up. All right, so let's check our dimensions here. So I've got 1 row, sorry, my bad. 3 rows by 1 column, 3 rows by 1 column. So they have the same dimension, I can do it. So this is going to be 5 plus 2 minus 2 plus 6, 1 plus 0. Right, so I'm going to add these up. 5 plus 2, that's 7. Minus 2 plus 6 is 4, and that's a 1. Okay. So far, so good with adding and subtracting. Alrighty. So our last bit to talk about here before we jump into other parts, our last bit is what we call a linear combination. linear combinations of matrices, right? So let's say I've got matrix A, and it's got a dimension that's the same thing as matrix B. Let's say they have same dimension. Okay, let's say I've got C and D are scalars. They're just constants, they're just numbers, right? So what I can do as a linear combination, I can say C times A plus or minus D times B. So watch out for your order of operations, right? So order of operations matters, right? What this means is I need to do my multiplication first. So I need to multiply by scalars first, and then I need to add or subtract. We call it a linear combination because adding and subtracting is a linear property, a linear process that we're working on. So C times A plus or minus D times B. Then I just add or subtract. So we're kind of combining these two different things. I still have to check the dimensions of A and B first. So let's do example 9. We're rolling right through this here. There's a lot of stuff to take into account, but we're good. We'll take it step by step. All right. So look what I have. Minus 2 times this. This is like my matrix A. Positive 3 times this. This is like my matrix B. So let's see, this is how many rows? So this is a 3-row by 3-column matrix. This is 3-row by 3-column matrix. So they have the same dimension, so I can add or subtract. So now when I want to do this linear combination of things, I have to first do the multiplication. So I'll do that first. So I'm going to go minus 2 times 2, minus 2 times 0, minus 2 times a minus 1, minus 2 times 4, minus 2 times 1, minus 2 times 3, minus 2 times 0, minus 2 times 1, minus 2 times a minus 1. See what I did? I just distributed this minus 2 to all of these terms here. Plus, I'm going to do the 3. I'm going to take the 3 and I'm going to distribute it to all of these terms here, just like we did when we did the scalar multiplying, right? This is going to become 3 times 7, 3 times 6, 3 times a minus 10, right? That's my first row. Second row, 3 times a minus 2, 3 times a minus 1, and then 3 times 5. My third row, 3 times 1, 2, and 3 times 3. Okay. Not a negative, I just put the multiplication by accident. Okay. I know it's a lot of work. Let's go ahead and do it. Next step, you multiply it through. So this is going to become minus 4, 0, positive 2, right? Minus 2 times 2, right? So this is going to be minus 8, minus 2, minus 6, 0, minus 2, and positive 2. That's this one. Plus, let's do this part here. So 3 times 7, 21. 3 times 6 is 18. 3 times a minus 10 is minus 30. 3 times minus 2. 3 times minus 1. 3 times 5. Here is 3. There's 6, and there's 9. So all I did was multiply it through. So I did the multiplication part first. Now I get to add the corresponding pieces. So minus 4 plus 21 will give me 17. 0 plus 18. 2 plus a minus 30 is minus 28. Minus 8 plus a minus 6, minus 14. Minus 2 plus a minus 3 is minus 5. Minus 6 plus 15. So it's 15 minus 6. 0 plus 3. Minus 2 plus 6. 2 plus 9. And we're done. Okay, linear combinations. Watch your order of operations. You do your multiplication first, right? And then you add or subtract. So let's try, do one more example for linear combinations. Yeah. So here, right, remember what we're going to do? We're going to take this 3 and I'm going to multiply it by these terms. Take this, I'm going to change this into a plus multiplied by a -4. So this is going to look like 3 times 5 is 15. 3 times a -2 is -6. 3 times 1 is 3. Plus -4 times 2 is -8. I find it easier to do adding than subtracting, so I like to multiply by a negative number. You don't have to do that. If you can keep track, you can multiply by +4 and just subtract these terms. You're going to come out at the same spot. -4 times 6 is going to be -24. -4 times 0. So I'm going to add corresponding pieces. So 15 minus 8, right? -6 minus 24 is -30. 3 plus 0. And that's our answer. Do the multiplication part first. So I didn't have to multiply by -4. I could have multiplied by +4 and then just subtracted. It would have just been 15 minus 8 minus 6 minus 24, 3 minus 0. You would have gotten to the same spot. Okay. Linear combinations. Of course, I'm going to give you guys a minute to finish writing that down. All right, so scalar multiples. Now let's talk about matrix multiplication. So let's see, that was 5. Let's do 5. So matrix multiplication. So let's say I have matrix A, and I want to multiply by matrix B. So let's say A times B, right? Well, I have some things I need to ask myself first before I can jump in and do that. So I have to check that the dimensions, they don't necessarily have to be the same, but it has to go like this. So this is row by column. This is row by column. Order matters. Order matters. So AB is not equal to B times A. Sometimes one of them will exist, but the other one doesn't. Because what happens is I check the row by column for A and the row by column for B. The inner dimensions must match. So the columns on A must equal the rows on B. My answer will be here. This is the dimension of our answer when I do this matrix multiplication. Now, this is important because, right, I often actually will say, okay, so if the inner dimensions match, I can do the multiplication. Then I'll find out what's the answer dimension going to be, and I'll box it out and I'll put little lines to remind myself, okay, because I need to speak out what happens, like how am I going to do this? So let's do something. So if I've got something like let's say A is equal to let's do like a 2 by 3 matrix. So I'm going to go A11, A12, A13. First row, first column, first row, second column, first row, third column. A21, A22, A23. Right, so I've got 2 rows and 3 columns. Okay. Now let's say B is a 3 by 2. That means I have 3 rows and 2 columns. So I'm going to go B11, B12, B21, B22, B31, B32. So here's my matrix B. Right, this is just an example so you can see when we do the matrix multiplication. So I've got 2 by 3 and a 3 by 2. So my inner dimensions match. So yes, I can do this. And my output, my answer is going to be in a 2 by 2 format. So my answer, I'll do it as a C. My answer was going to be C11, C12, C21, C22. Oops, that's a C. 2 by 2. And it helps me because how we do our matrix multiplication is it looks a lot like our dot product. Actually, it is our dot product. So A times B looks like a dot product. But it goes like this. I take the first row and I multiply it by the first column. Times first column. And I add up, I do the dot product. I'll put a big dot there. Dot product of the first column. So first row dot first column, right? Then I do first row dot second column. Okay. Then I do second row dot product with the first column. Okay, and then second row, second column. And that's how we build up a 2 by 2, right? So first row, first column, first row, second column. The process by which you multiply also tells you the position that you're going to put your answer in. So if I multiply the first row by the first column, I'm putting my answer in the first row, first column position. If I multiply the first row by the second column, I'm putting my answer in the first row, second column position. See how that works? It's kind of nice because if you say it, this is how I do. I say it in my mind, and then I know where to put the answer. Let's use our A1s, B1s, and all that. So A times B, we've already said we can do it because the inner dimensions will work, and we now have an idea of what the output is going to look like. So my dot product, remember, so my first row, first column says A11 times B11 plus A12 times B21 plus A13 times B31. This is all in my first row, first column position. First row, second column is going to look like A11, B11, oops, A1, B12, sorry about that, plus A12, B22 plus A13, B32. Right, that's my dot product. I'll do it again for my second row, first column. 21, B11 plus A22, B21 plus A23, B31. And then my second.
You wrote second row, second column twice.
Ah, I did. I'm sorry. That's what whiteout is for. Thank you. Yeah, I'll throw those mistakes up to see if you're paying attention. Not my fault. First column. There you go. Thank you for telling me. Second row, first column. Thank you. All right. But I did this correct, right? So second row, first column, B1. Yeah, good. All right. So then here, second row, A21, B12 plus, A22, B22 plus, A23, B32. And then this makes up our matrix. We'll do examples so you can see. This is just like, you know, ideas, right? And then we'll actually do the product and see how it works. I'll let you guys finish doing that. You guys all set with this and ready for, who needs more time on that? Writing down. Good. All right. So let's take a look. So I'm going to do, is this product possible? Why or why not? So let's check our dimensions. So this is 3 row by 1 column. Here we have 3 rows by 3 columns. I check my inner dimensions. Oops. No, there's no match on my 1 does not equal to 3. So no inner dimension does not match. Okay. So this won't work. Let's just do it. I'm gonna, you know what, I'm gonna watch this. I'm gonna switch it out. So I'm gonna go 2, 4, 0, 0, 1, 1, -1, 3, -1. Let's say I gave you this instead, 2, 6, 0. Right, so this one is not possible. Nope, can't figure out what the product is, and that's not possible. But if I did, so this is A times B. Now if I do B times A, let's see what it looks like. So this is a 3 by 3. This is a 3 by 1. My inner dimensions will match, and my outer dimension, my answer will be in a 3-row, 3-column answer. So this one will work. Okay, this isn't what we were asked for. If you're asked for this, that's, you either can do it or you cannot. Okay, this is not, A times B is not equal to B times A. I just wanted to show you that sometimes, you know, this is what it will look like. Okay, let's check this one out here. What's the product here? So let's just check. So how many rows? I've got 2 rows and I've got 3 columns. Here I have how many rows? I've got 3 rows by 2 columns. Okay, so let's check. So the inner dimensions, but the inner dimensions match, so I can do the product. And my answer is going to be 2 by 2. 1, 2, 2, there. So that's my answer is going to be a 2 by 2 matrix. 2 by 2. So let's go ahead and do that and see what that's going to look like. So remember our process. I'm going to take the first row, first column, and multiply these out. So 1 times 2 plus 2 times 4 plus -1 times -3. First row, first column. Okay. First row, second column. 1 times 1 plus 2 times 2 plus a -1 times +1. First row, second column. Second row, first column. -2 times 2 plus 3 times 4 plus 0 times a -3. Second row, second column. -2 times 1 plus 3 times 2 plus 0 times 1. Okay. See how when you say it in your mind, first row, first column, that tells you where to put the answer in the first row, first column spot. So let's add these up. So this is a 2 plus 8 plus a 3. So -1 times -3 becomes +3. So this is a 13. This is a 1 plus 4 plus a -1. So this is a 4. This is -4. This is 12. This is 0. So this is 8. Right, -4 plus 12 is 8. This is -2, 6, and 0. So that's 4. Then that's our answer. Everybody see how we did that? Everybody good with that one? It's a lot of stuff to take in. You guys are going to be fine. We're going to practice it. We'll have plenty of time to practice as we go. Even if we don't get to the classwork today, we'll have time to practice it. Okay. Right. So our last topic I want to talk about here's what's called an inverse. So this is important because an inverse not every matrix is going to have an inverse. So let's first write that. Not every matrix will have an inverse. Okay, so first off, that's an important thing. We have to know that not every matrix is going to have an inverse. If we want to be able to take an inverse, usually it happens with square, what they call square matrices, which means I've got a 2 by 2 or 3 by 3 or 4 by 4 or 5 by 5. They have to have the same dimension on rows and columns, right? So the same number of rows as I have columns. It makes it a square matrix. Okay. So inverse of a matrix. Now to take the inverse, let's say I'm going to take my matrix is A. I'm going to call this A, B, C, actually going to spend like a whole chapter talking about inverses, so I'm not going to go into too much detail on here, but I'll tell you how to do it, and then we'll come back to it later. So if I want to take the matrix now to find the inverse is called A minus 1. That's our inverse of A. And how that looks is this. I go 1 over the determinant of A. I'm going to talk about, what is that? I'm going to talk about that in a minute. Times, what I need to do is, I have to switch A and D, so this becomes D and A, and I have to negate C and B. You've been doing the determinant when we did our cross product. So the determinant of A is, we did with our cross products, right? So this is A times D minus C times B. Okay. If this is equal to 0, I can't get a I can't get an inverse, right? So if determinant equals 0, no inverse is possible. Also, you can see I can only take a determinant on a square matrix, so that's also why I can only do an inverse on a square matrix. So this is how we need to think about it. This is my second to last topic. We've got one more topic after this. It's pretty straightforward. All right, so example 13, matrix A is 1, 2, 3, 4. 1, 2, 3, 4.
Wait, go back for a second. I'm sorry.
Yeah, you bet. What's that? Is that good?
Yeah, thank you.
Sure, no problem. All right, example 13, you've got matrix A is 1, 2, 3, 4. What about what's the inverse? A minus 1. Okay, so that means I need to find my determinant. It's 2 by 2, 2 rows and 2 columns. So I can potentially find an inverse. So the determinant of A is going to look like, so I have to cross multiply. So it's going to be 4 times 1 minus 3 times 2. So 4 minus 6 is a minus 2. Okay. So now, right, remember our inverse, A minus 1, was going to equal to 1 over the determinant times, and I need to swap these values. So it's going to be 4 and 1 and minus 3 and minus 2. So I swap 4 and 1 and I negate 3 and 2. I'm going to plug in here. So this is going to become minus 1 over 2. So it's, oops, sorry, 1 over negative 2 times 4 minus 2 minus 3, 1. I could leave it like this. That's totally fine. I can distribute the 1/2 into here. So this is going to become 4 times a minus 1/2 becomes a minus 2. Minus 2 times minus 1/2 becomes positive 1. Minus 3 times minus 1/2 becomes 3/2. 1 times minus 1/2 becomes minus 1/2. These are equivalent. They're both fine in terms of inverses. Okay. Good with that? I will scan these in later and then upload it to SOAR so you can see it. There's a concept with our inverse, right? If I multiply my matrix times its inverse, I get back what we call it I. I is called the identity matrix. And the identity matrix is a square matrix that has the same number of rows and columns. And what it means is it's got a 1 on the diagonal and zeros everywhere else. So this is a 2 by 2 identity matrix. If it was 3 by 3, it would look like 1, 0, 0. The identity matrix is really important. It's kind of like like a placeholder in a lot of ways. It's also used and talk about other stuff in linear algebra, which things we're not really going to get into so much, but it's important that we know what an identity matrix is. So ones along the diagonal, zeros elsewhere. And if I multiply a matrix by its inverse, I get it, the identity matrix. This is actually one of the methods for being able to figure out the inverse of it too. You kind of, you start here and then you go, okay, well, how do I get this to look like that? And it's a whole process that it's beyond the scope of this class, but this is another method for being able to solve for the inverse. So that's identity matrix. There's also something I want to throw out too. So if I do A times B, two matrices, and I want to take the inverse of their product, that's the same thing as saying the inverse of B times the inverse of A. Now I have an example, which I'm not going to go through in class because it's kind of long, but example 14 actually does this whole thing out, but I'm not gonna do it in class. I'll write it up, and then I'll when I scan it in, you'll be able to see this kind of proves it to you that that's actually true. Because I want to cover one last thought before we go. Something called a transpose of a matrix. So if I have matrix A, right, and it's got a row by column, my transpose of A is called A. Sorry, I jumped ahead of myself. It's written as A with a T, like this. AT means the transpose of A, and all we've done is we've switched the rows and columns. Okay, so it looks like this. This is going to become a column by row. We'll do some examples so you can see transpose is important. It comes into play when we're trying to do transformations, and it's used in things in linear algebra that are kind of outside the scope of what we're trying to do. But transpose is an important idea. So 15, 16, 17 example are going to be able to show us. So if matrix A equals 1, 2, 3. So let's just talk about it. I have one row. Question. Yeah, what's up?
Remember earlier when you were saying when you can't add you can't multiply if the inner dimensions aren't the same.
Right.
If you transpose, like say you had A times B, if you transpose B because the inner dimensions weren't the same, could you then find the answer?
Yeah, but it's different. So you're right. So that would be a different example. That's like saying if I want to multiply 3 by 1/3, let's pretend I can't do it. 3 by 1/3. Well, I'm just going to switch 1/3 into 3. So 3 times 3. Then see how 3 times 1/3 is different than 3 times 3. So you're right in terms of if I transpose it, I'll get the right dimension, but then by multiplying it through, I get a different answer. It's a different product. So that's when we say when we multiply matrices, like A times B is not equal to B times A. Yeah. Okay, so you have to be careful, but we are going to use the idea of a transpose, and we're going to use matrix multiplication a lot when we do transformations. Like when I want to, do a bunch of transformations together, I'm going to basically multiply all those matrices together, and then I'm going to apply it to something, right? So we're kind of chapter 2.2 is building up like a vocabulary and like a set of basic functions, right, that we're going to be using to do other more complicated stuff. But you're right. I mean, so if I transpose it, I'll get the dimensions right, but it'll be a different product than what we had asked for. You know what I mean?
Yeah. Okay.
Yeah. So let's do this. So if matrix A is 1, 2, 3, that's a 1 row by 3 column matrix. Our A transpose is going to be a 3 column by 1 row. I'm sorry, 3 row by 1 column matrix. So this says I switch the rows and the columns. So AT becomes, I have the first row becomes my first column. Excuse me. So you see how this had 1 row and 3 columns. This has 3 rows and 1 column now, right? I say it in my mind. So this one here, right? So our dimensions here are going to be this, if A is this right here. So this looks like I've got 3 rows and 2 columns. My transpose is going to have 2 rows and 3 columns. And so I say it in my mind like this. I go, okay, transpose. First row becomes first column. Second row becomes second column. Third row becomes third column. See how I did that? Let's do that in different colors. I love colors. So here's the first row. Here's our first column. And I'll do blue. Here's our second row. Here's our second column. I'll do, actually, you know, I'll make that light blue so you can see it better. Second row, second column, and then third row becomes third column. See how those are setting up like that? Everybody see how we're doing that transpose? This one here, right? I've got 3 rows by 3 columns. So my transpose is also going to be a 3 by 3. So this is where you say it in your mind becomes even more important, right? So let's do this. So this is my first row becomes my first column, 2, 0, -1. My second row becomes my second column, 4, 1, 3. And I'll have a green. And then my third row becomes my third column. Do you guys see how we did that? So this is still a 3 by 3. 3 by 3. So the dimensions didn't change, but the position did. This is our A transpose. Okay. So we're kind of building up like ideas on how to do stuff, right? And what does this vocabulary mean? Like I said, I'll do example 14 offline and I'll scan it in so you can just see what it looks like. There's kind of a lot of stuff with example 14. Transpose is important, inverse is important, all of the matrix multiplication is important. All of these things come into play a lot as we do transformations. Okay. And then don't worry about the classwork for 2.2. We'll have time to practice it later. Okay. All right, you guys, sorry I talked for the whole period. I thought I would have time to break, but okay. See you guys later. Have a great day. And let me know if you can't access anything on our website, and I'll take a look at it because Canvas was doing things. See you later.